Yeah, so we continue talking about gradient descent and its theoretical guarantees of the algorithm, and a little bit about convexity. We are going to talk also today. Okay, so let me recap what we did last time. So we defined a gradient descent algorithm that is designed to find the local minimum of a function. Yeah, so we're assuming that we have a function f, the function that maps the dimension of vectors into real values, and we want to find some point x in the dimensions that brings the value of the function to the minimum. And we're assuming that we don't have any constraints on this x. Yes, and the algorithm we discussed last time is a very simple and basic form of gradient descent, which is basically an iterative algorithm. And then it has a very basic idea, intuitive idea of starting from some point, x0, arbitrary point or randomly chosen point, or maybe some smartly guessed point. And we start the process of walking step by step, such that at each step, we are walking in the direction of the greatest descent of the values of functions. And the size step we are doing is parameterized by parameter eta. So after, and the last time we actually discussed how to find this direction of the greatest descent, which is given just by the gradient of the function minus of the gradient of the function. Okay, so this is the intuition behind the algorithm. So the algorithm proceeds in iterative steps, and after some t steps, it stops and reports a point which is just the average point in the trajectory the algorithm walked, or maybe the last point, or maybe the point with the smallest value among all the points the algorithm visited. So there are many variations how the point can be reported. Okay, and there are many also variants of the gradient descent algorithm itself. This variant is called kind of first approximation, first order approximation. There can be added some more variants like second order approximations and more, which a little bit accelerates the convergence rate. But I'm not going to talk about all this here, but this is like a huge field of optimization, and many beautiful results are there. Okay, so so we're going to look at the theoretical guarantees of this algorithm. So there is a theorem, and theorem says that if we assume that the function f has very nice properties, so if this is such a function, so it's guaranteed that after a certain number of steps and defining the step size in a certain way, the resulting point, the algorithm will stop and return the point which is very, very close to the optimum point. So indeed, the algorithm will find the minimum. So what are these properties of the function? So I'm going just to go slowly, one by one. From the first side, these properties doesn't make much sense. But actually one needs to see the proof of the theorem to see that, yes, these properties really are helpful to get some theoretical guarantees. So what are these properties? So first of all, we need to assume that f is convex. I'm going to talk about what is it a little bit later. For now, just assume, okay, it's some nice property of a function. It's not so rare property. Really many functions are convex. And the function should to be row-Lipschitz. What does it mean? So the formal definition is that for any point in the dimensions, the gradient of the function of this point is bounded by a row. So intuitively, what it means that if we are staying at any point x, and we are trying to go any direction from this point, and we are measuring the rate of change of the values of f along all these possible directions. So if the speed of change is bounded by rho, so we say that function is rho Lipschitz. It means that the change of the values is bounded starting from any point. Yeah, so the function is not crazy behaving at some area. Yeah, the rate of change is bounded and it's kind of smooth. Kind of function is kind of smooth, we can say. So this is a nice property to have. Another assumption is that if we know that the optimum, so we are looking for the optimum point. Yes, we are looking for the point x star, let's denote it x star, such that the value of f at x star is minimized, is the smallest possible value of f. So if we know somehow from the prior knowledge that this point x star we are looking for, it is inside the ball of radius r around 0, yeah. So, and it's always correct. It's always, yes, the point we are looking, it's located somewhere. So of course there is some r such that x belongs to this ball of radius r, right? It can be huge, but there is always such an r. It's just the length of this x star. So if we assume that we know this bound r, and we also assume that the process of the iterative search for the minimum of the gradient descent starts from some point in this ball. Yeah? So x0 is inside this ball. Somehow we use the prior knowledge to know that the optimum value somewhere in the ball of radius r. So let's start from any point inside this ball. So if we know all these things, so if we run this algorithm of gradient descent, so for any epsilon, so we can now define any epsilon. You can define epsilon 1 or 1 over 100, for example. Yeah? So for any epsilon, if we set the number of steps t in the algorithm to be at least this number, what is written here, which is r squared, which is the radius of the ball, rho squared, which is the rho constant of the Lipschitz mass. Epsilon squared is the epsilon we chosen. So all parameters here are defined at this stage. Yes. So also notice that the smaller the value of epsilon, the larger the number of steps we need to take. Yes, because if epsilon is small, smaller than 1, so dividing by the small number smaller than 1 increases the value of t, right? So now we know how many steps we need to take, this number, r squared, rho squared divided by epsilon squares. And now we need also to set the step size we are taking in the iterative algorithm. So the step size should be defined as given in this formula, square root of r squared over rho squared times t, which we can put t inside the formula from the previous definition. And we get that the eta should be epsilon over rho squared. So if we think about rho, some parameter, some fixed parameter, yes, so it doesn't change a lot. So what changes here is epsilon. Yes, the smaller the epsilon, so the smaller should be the step size. And actually, step size should be pretty small, as we see here. And it kind of makes sense because we don't want to make large steps and to miss the minimum point, to jump somewhere like far from the minimum point. So the step size should be small. So if we define this number of steps t.
So two things. One, if for some reason I'm able to choose x0 that is within the ball defined by the length of x star, then the length of x star would become the R square, right? So
yes, the length of this X star contributes to the number of steps you need to do.
yeah, interesting.
Yes.
And another thing, when you said you substitute t with r square, etc.
Yeah.
Then because it works because it's bigger, right? It's so you
Yes.
substitute something smaller, so it's bigger.
Yes.
Because yeah, right.
Yes.
Mm.
It
Also,
is.
how do you get this eta equals square root of r squared by rho squared t?
You substitute r square instead of t, you write r square.
Yeah, before that, how do we get this? How do we know?
Oh, that's a requirement.
No. Yes, it is a requirement, but it follows from the proof of the theorem.
Ah, the t is bigger than that. That
T
with
and also eta.
okay.
Eta also follows from eta equals to the square root of r squared over rho 2 times t. It follows from the proof of the theorem. We don't see it here. And just later on, the last step is to get epsilon, to install epsilon inside. So it follows not from the theorem, but from here, from these substitutions. Yeah, I'm not showing the theorem. It's a little bit intricate.
Okay.
It's not so easy, difficult to follow. Everyone here would understand for sure, but it will take us maybe 2 academic hours to cover. Yeah. So yeah, so if we have, so under these assumptions and fixing some epsilon, the theorem says us how many steps and what step size to take. Once we set
so Lifshitz, it's probably enough that it's Lifshitz in the ball of R, right?
So yes, so now everything goes down actually to assuming that it's convex and it Lifshitz in the ball of radius R. Yes.
Yeah. So
yes, we are constraining ourselves implicitly here to the ball of radius R, right? Right. So yeah, so taking all these assumptions and setting all these parameters, the theorem says that the algorithm will output x hat, point x hat, such that it will be first of all inside this ball of radius R. This is what we wanted because our x star there. So of course our x hat should be there. And such that the value of the function at x hat is very, very close to the value of the minimum of this function. Yes, this is what we wanted also. Fx hat minus fx star are very, very close, epsilon. And this epsilon, this is the parameter you choose. This is the quality of the approximation you want. The highest quality of approximation you want, the largest the number of steps you need to do, and the smaller the step size, of course. And implicitly, what we are showing here actually is that this x hat is a local minimizer of the function. This is what Ethan exactly told, that x hat is a minimizer in this ball only. Yeah, so this is a nice theorem which gives exactly the convergence rate and gives the guarantee that the minimum will be found, which is not so trivial, right? Because there are so many assumptions. Yeah, so there are other versions of this algorithm that reduce some of the assumptions, but mostly all these theoretical guarantees that we can obtain, most of them are making a kind of heavy, not heavy, but kind of, yeah, heavy assumptions about functions, which are not always satisfied in real case situations, where even convexity of f we cannot guarantee. And even if we can guarantee, and even if we know that the function is a row Lipschitz, it's not so easy to compute this row. Yes. from this definition. How can we show? It's not so easy even to show. And if we somehow can show, we can compute it that efficiently, maybe.
What is Lipschitz? What does that mean?
It's a name of a person.
Yeah.
Yeah, I understand, but when you say like rho minus Lipschitz, what does that mean?
Yeah, so it means that if we are looking at, so it's a property of a function that says intuitively that the rate of change of a function is bounded from any point.
So the gradient on the right, you see the gradient of f is less than rho. The length of the gradient of f is less than rho. And we call that rho Lifshitz, in honor for Lifshitz.
Okay, got you. Thanks.
Yeah. And
So it's not really an equation. It's just a naming of that.
Yeah, it's mathematicians. That's what they do.
Yeah, no, I understand. Thank you.
And this is one of the most difficult names in math to write, actually, from the memory. I never write it correctly. I should consult Wikipedia. Yeah.
There's a lot of very, very high challenges associated with mathematics, like how to write Lipschitz.
Yeah, so French names.
Yeah, I had an electromagnetics professor that would take points off if you didn't capitalize units that were named after, some earlier inventor. So it was interesting.
Yeah, serious.
Okay, so the last thing I didn't explain is what is convex. Okay, so what is convex? So convexity is a very big field in math, actually, and there is even a separate field for studying it. It's called convex geometry. Many beautiful results and ideas, and it's really huge. Like I know at least like 5 courses in the university covering these topics. But we need only like the first basic definitions of convexity of a function. This is a very important notion in machine learning also, because once the function is convex, we can usually prove many nice things. Yes, one of them is convergence of gradient descent, and some others which we will maybe meet later in this course, in these meetings. So what is convex? So what is the convex function? Like intuitively, if we are looking just at the function of one variable. So here is a graph. Yes, there is a small like the picture of what's going on. So let's say we have a graph, we have a function, and we have so we can draw a graph of it, right? If we are just in univariate case, so we can draw a graph of a function. The thing that is depicted here in this small picture. So now let's take any 2 points, x and y, in the x-axis, and let's connect f of x and f of y. Okay? So you see f of x is the point on the graph, f of y is the point on the graph. So just connect these 2 points with a straight straight line, and look at the graph of the function between these points x and y. So if the graph of the function lies under this straight line connecting f of x and f of y, so the function is convex. If this is true for any 2 points, so the function is convex. Okay. And in the formal definition, generalizing into d dimensions, so the function f from d dimensions to real numbers is convex if for any 2 points x and y in d dimensions, and for any scalar lambda from 0 to 1. So if we are looking at the point, some points lying between x and y, which is given just by this formula. So lambda times x plus 1 minus lambda times y is just the description of some point lying in the line between x and y. Yes, this is the formulation of some point between x and y. So if we are looking at this point and we are looking at the value of the function at this point, so this value should be smaller than the point lying in the straight segment connecting f of x and f of y, which is given by this formula on the right side. Okay, it's a little bit confusing. It requires some time to look at it and to understand that this mathematical formulation is just formulating the intuitive definition we gave before. Right? The graph of the function is below the straight line connecting any 2 points. That's all.
Note that if f was a linear transformation, then you would get the same thing with equality, right?
Yes, right.
So so you can think about it as a relaxation of the linear transformation requirement.
Yes. So why I wanted to talk about these convex functions? Okay, because it's one of the assumptions in the theorem, and also because convex functions have very nice property. In convex functions, the local minimum is also a global minimum. What is local minimum? Local minimum is if you're looking at some small area in the domain, and we can find some points such that its value in this domain is the smallest one among all the other points in this domain. So this is a local minimum, right? Looking at some bounded region and saying, okay, this point is the smallest in this region. But it's not necessarily the global minimum. Yes, if we are looking at the whole domain of the function, so maybe there will be some point which has smaller value, right? So, but for convex functions, it's not true. For convex functions, if you find the local minimum, it also for sure is the global minimum. So convex functions have only one minimum, which is the global minimum. And this is nice because what we proved before, we proved that the gradient descent algorithm finds x hat, which is a local minimizer inside the ball. But if f is convex, it's also a global optimizer. So actually gradient descent finds optimal, global optimizer. Okay, so this is the connection to the gradient descent. So how can we prove that for convex functions, local minimum is also a global minimum? It's a very nice and short proof. So let me start proving it. So let's x start to be some local minimum, some point such that we know that is a local minimum. And we want to show that this local minimum is also a global minimum. What does it mean that x star is a local minimum? It means that there is some region of points, let's say n, in Rd, such that x belongs to this region, in such that the value of x star is the smallest among all other points in this region. Yeah, so this is what is written here, that for all x in this region n, f of x star is smaller, or at least not greater, than f of x. And I depicted this region in this picture by these brackets. Yeah.
So by region here, you mean, in the general case, you just mean a ball, right?
A ball, or it's not necessarily a ball, can be any bounded connected maybe set. I don't know if we need actually definition of a restriction to the ball. Maybe
yes,
some neighborhood.
No, you're right. It could be, certainly it could be like a closed ball or an open ball, or it could be any reasonable thing. But what I'm trying to say, that you're proving here something that applies to RD, not to R, right?
Yes, to RD. Yes.
Yes.
And the small picture here, I did it for R because it's simpler to depict.
Yeah.
Okay, so we have this x star. This is the local minimum, and we have this square brackets which depict or denote this region N. And we know that in this region, X star has the smallest value. F of X star has the smallest value. No other point has smallest value than X star. And we want to show that X star is actually the smallest point, like among all other points in RB. Okay. There is no any other point with strictly smaller value than X star. So how we do? So let's assume by contradiction there is such a point, X star, X tilde. Assume by contradiction we have some X tilde somewhere, such that the value of F at X tilde is strictly less than the value of F at X star. And we show that it cannot be true. It's not possible. Why? Because if this is true, so we know, and we know that F is convex. So we know that for any scalar lambda, if we take some point between X star and X tilde, yes, this is the point, lambda times X star plus 1 minus lambda gamma times X hat, X tilde. This is sum of the point between X star and X tilde. And we measure the value of F at this point. So we know it should be bounded by the value of this point, lambda times F X star plus 1 minus lambda times F X tilde. This is just by the definition of convexity. So the first summand stays the same. So it's just lambda times F X star. And the second one, F X tilde, we assumed it's strictly smaller than the value of F at X star, right? So
yeah, that's a contradiction.
Yes, not yet. That's assumption. So we assumed, so this sum we assumed is strictly smaller than the lambda times F X star plus 1 minus lambda F X star, which equals to F X star. So what we got here? So we got that for any point that lies in the in between X star and X tilde, the value of this point of F is strictly smaller than the value of X star. So how we get a contradiction? So we can choose this. So this is true for any point in this interval between X star and X tilde. So we can choose lambda small enough such that this point between X star and X tilde lies inside the region N.
Yeah.
Right? We can choose that lambda be so small such that this point lies inside the region N. And then we know, so we obtained that we can find some point in the region N with the value strictly smaller than the value of F at X star. And this is a contradiction because X star is the minimizer in the region N. So the local minimum is also a global minimum. There cannot be any other point anywhere with the value smaller than X star. Yeah. So this finishes the
very nice. Just one comment about this. So F is, if you think about learning, F is the loss function. So having a single global minimum means that you, in some sense, learn in the best way globally.
Yes. And for some algorithms, learning algorithms, we actually can find the global minimum, right? For this linear learning, right? Linear hyperplane separation. We can find it global optimum.
So how do you use this to adjust the weights in a neural network when you're going through training?
Yeah.
I mean, do you just, you know, all the weights of all the nodes based on this, or do you focus on some specific ones? Right.
We'll get there, Jim, but
okay,
it has to do with the gradient. So updating the gradient is done. Is another thing that we'll talk about, and that's how you do it. So.
Yeah, so that's part.
Okay, I'll be patient.
Yeah, we just laid down, the math foundations for what's going on behind the scenes when someone is training a neural net. So what is actually going on there is that there is some function f that is probably convex that we are optimizing and optimizing it through the gradient descent algorithm. So now how to apply to a specific case of a neural nets, it's a separate talk. And the algorithm is called backpropagation, which actually implements gradient descent in the realm of neural nets. You can look at it like this.
Okay, thank you. Yeah, this has been very interesting.
Yeah, thank you.
And that together with the backpropagation, you'll get the entire picture.
Yeah. So we'll talk about it in a few more talks from now.
Yeah. Okay. Thank you so much. That was excellent. Very interesting.
Yeah, very nice. Thank you.
Thank you.
Thank you. Bye-bye.
Bye-bye.